Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. And so far, we have looked at the Euler method. And we said that the basic idea is that we create a sequence that converges to the value of the function at each point. For example, if I want to solve this differential equation, y prime equals negative 1, and then the initial condition y of 0 is 1. If I want to solve this and find the value of function at 0.5, I create a sequence that converges to the value of the function at 0.5, and then I accelerate it using, so I can easily just try to find the value using the Euler method, and gives me a sequence of values that converges, and then I can accelerate the convergence using a Richardson acceleration. This was the whole idea. And not only we can apply it to Euler method, but as we will see later on in these lectures, we can apply this simple idea to any type of method for solving ordinary differential equations. So we always create a sequence that converges to the value of the function, and based on the method, the sequence could converge fast or slow, and whatever sequence we get, we can always do a Richardson acceleration to increase the speed of convergence and reduce the order of magnitude for the error. All right. And then we said that the problem with such solutions such as exponential function e to the negative x, the solutions that have a very rapid increase or decay, is that as we increase the interval for x, as we try to find the value of the function at points farther away from the initial point, which in this case is 0, the error is also proportional to the length of the interval. And in order to avoid the error getting larger by getting farther away from the initial point, what we can do is that as we progress and solve the value of the function at later points than the initial point, I can take for solving the function at some later point, I can take the previous point that has already been solved as the initial point, and then the interval between them always stays small. So that's a benefit, because then I can get away with this increase in the error. And that's always a good idea. Not only this, but it also helps with the stability of the solution. Again, stability here means that as the interval gets larger and larger, the error doesn't get larger and larger. We kind of control the error in a global sense. All right. So here's another example. Example 2 in this. Okay, this should be example 2. In this example, y prime is y over x and y of 1 is 2. So the initial point is x equals 1, and the value of the function, the initial value is 2. Okay, but note that here y prime equals y over x. So this function f of x and y has a singularity at x equals 0, right? So if we want to solve the initial value problem, we should look at the interval that doesn't have this singularity. So it's the interval that we're going to solve for is from 1 and later points, so it doesn't include 0. So we are safe. We know that our numerical method is not going to have any problems. If we want to solve for intervals that do include x equals 0, then we have to work a little bit harder to look at the behavior of the function, the solution at x equals 0, around x equals 0. Whether it's continuous, does it have limit or derivative or whatever. So singularities are always important when we're solving differential equations. But here in this example, I'm just considering that the interval that I'm solving for does not include x equals 0, which is my singularity. Now this differential equation has a very simple solution, y equals 2x. And if you're wondering how I solve this, I use the method of separation. So y prime is dy over dx. And then because f of x and y can be written as the multiplication of a function, just of a function of x times a function of y, I can do method of separations. I integrate over y separately, integrate over x separately, and we end up with this. Y of x equals 2x. It satisfies the differential equation, it satisfies the initial value and therefore it's the unique solution of the equation. And now I'm trying to find the value of y at 1.5, and it should be equal to 3. But let's look at the code. And again, all the codes that you're going to see in this lecture and in the next few lectures, the structure is exactly similar. So we start with our derivative function, which defines the y prime as a function of x and y. Okay, so it's a functional interface. If you recall, x and y goes to y over x. X is a double number, y is a double number. And after defining the interface for f of x and y, we create an ODE solver object. ODE solver, new ODE solver, and in the ODE solver's constructor we pass the function, the initial point, which is x equals 1, and initial value y of x equals 1, which is 2. Okay, now I'm setting up a timer just to see how long it takes to solve. But what I'm interested in to solving from 1 to 10 interval. And let's say I want to solve for 20 points, all these red dots. Okay, so what I do, I create an array, x equals linear space of from 1 to 10, 20 points, and I create calculate the exact value because I already know the exact solution. Array func apply t goes to 2t and apply to the array x. Okay, so I'm calculating 2 of x for all the values of this x array, and then the y Euler is simply calling getting the ODE solver object and calling the Euler method. And if you recall, this Euler method takes in an array of values and find the solutions at all the points of this array. Okay, and then returns an array of solutions, this Euler method. And we also implemented the trick that we discussed. So now we just create a plot. The blue color is the exact, y exact, the red color is Euler. I render the plot, x label, y label. I turn the markers on the red plot, and then set the line width on the red plot to 0. So I just want to see the dots, the markers, the points, not the lines that are connecting them. And set the font to 17, for example, and show it in a separate window. And we get this. So the blue is exact, the red is Euler plus Richardson acceleration, fourth order, and we see that we get almost a perfect result. Okay. Now the next example is very interesting because so far all the differential equations that we have looked at, y prime equals negative y or y prime equals y over x, these were kind of linear in y. So we actually had a linear ordinary differential equation. But in this example, I have a nonlinear differential equation, y prime equals minus y squared. And it's an initial value problem. Okay, so this is example 3, and so if it's nonlinear in x, for example, if it was y prime equals minus x squared, we do not call it a nonlinear equation because nonlinearity defined based on y, the function that we're looking for. Okay, but as long as we can write it in the general form of y prime equals f of x and y, we really don't care about the format of the f of x and y. It could be linear in x, linear in y, nonlinear in x, nonlinear in y. We don't really care because we can always use any of the numerical method and exactly solve it. Okay, of course, as long as we don't encounter any singularity. So minus y squared doesn't have any singularity in x and y, so we're good. Y of 0 is 1, so the exact solution, and again we can use method of separations to exactly solve it, is 1 over x plus 1. So there is a singularity at x equals negative 1, but we don't care about that because we're solving from 0 to infinity plus infinity. And for example, y of 1.5 is 0.4. Okay, And as I mentioned, Euler method does not care about linear or nonlinear expression for f of x and y. As long as we can write it as y prime equals f of x and y, we can always be able to, we are always able to solve it. And here's the code, and again the structure is exactly similar to the previous ones. Actually, we just changed one line of code, which is the definition of f of x and y, the derivative function. Everything else is exactly the same. So I hope you appreciate how nice this is, because jumping from one problem to another problem, we only need to change one line of code in principle. So we define our f of x and y, which defines the derivative function or y prime. X and y goes to minus y squared, and then we create our ODE solver, passing the function, the initial point x equals 0, initial condition y equals 1, basically y of 0 is 1, and then set up timer, and then create an array of values from 0 to 50, 2000 points. And for this x array, I calculate the exact function. So t goes to 1 over 1 plus t for x, okay, for this array, 2000 points. And then I create a coarse array that has only 50 points, from 0 to 50 points. So I don't want to solve the ODE for 2000 points, because I just want to be able to differentiate these markers that I put. So I solved the ODE for only 50 points over the same interval, 0 to 50, okay? And the solution of the ODE is just taking the ODE solver object and calling the Euler method on the points, x Euler, which is 50 points, and then creating the figure, plotting it, setting the line width to 0 for the red one, setting the markers on, and then showing. And as you can see, we see the exact result. So the point here was that we don't care about the nonlinearity of the f of x and y. As long as the left hand side is just y prime itself, then we should always be able to solve this differential equation numerically. Okay, there might not be an analytic solution, but we don't really care. All right. Now, we started with the Euler method, and we said that it's the simplest solution. Nobody uses it because the error behavior is 1 over n, which is very bad. But the trick that we had up our sleeves was that we said we don't care about the behavior of error, which is 1 over n. I create my Euler sequence, and I then accelerate it using a fourth order Richardson. Suddenly, the error becomes 1 over n to the 4 or n to the 5. And I know that my Euler plus Richardson converges pretty fast. So that was the trick. But then there is always a trade-off between evaluating the function, how much computational cost there is for evaluating the function, and how much it is for applying the acceleration methods like Richardson, fourth order, etc. Okay? And if the computation of the function doesn't have much cost, it's pretty fast, then it's better to, instead of starting with Euler, we start with a method that already gives us a better error estimation, right? Instead of having 1 over n, we have 1 over n squared, 1 over n cubed, etc. And as you probably can guess, it always involves more evaluations of the function. So Euler was simplest because we only had one evaluation of f of x and y. But in a higher order method, or methods that have basically they start with a better error, we always get more and more evaluations of the function. Okay, so there's always a trade-off, which method to choose and which acceleration to go for. So the next method is the midpoint method. And okay, so maybe before starting the midpoint method, I want to point out one also important point here. That in the Euler method, we saw that, okay, we say f y prime is y of x plus h minus y of x over h, right? And then we can find the value of y at some later point. And now what happens if f of x and y does not depend on y? Then the problem is y prime equals f of x. And the solution is just an integral, right? From the initial point, which is a, to some point x. And if you apply the Euler method, to, instead of calculating the integral directly, you solve it as a differential equation. What happens is that the Euler method in this case becomes exactly equivalent to the integration based on the forward rectangle approximation, because we are doing the forward approximation for a derivative. Okay, so basically the area of each subinterval becomes h, the length of subinterval, times f of x. There is no y here, right? The value of the function at the start point of the subinterval, and this is exactly the definition of the forward rectangle. If I go back to the numerical integration case, in the forward rectangle, the area of each subinterval is the length of the subinterval h, or delta x, times the value of the function f of x at the start point. And if the f of x and y in the Euler approach doesn't depend on y, we end up exactly with this solution. And we in the numerical integration, we also said that this has a very poor convergence. The error is very bad. But the other case is backward integration, which in the ODE language, it has a method called backward Euler method, which I'm not going to discuss because it's very similar to the forward method. But then we said that there is another way, and that's the center method, or the midpoint method. Here we approximate the area by taking the value of the function at the midpoint of the interval. So if the interval is xi plus 1, we calculate the value at xi plus 1 over 2 times h, or delta x. And we said that this center approximation has a better error than the forward or backward. So here, for forward or backward, if the error is 1 over n, and n is the number of subintervals, the center is 1 over n squared. All right. Now back to the ODE case. This center approximation has an equivalent ODE solution, or ODE method, called the midpoint method. So in the midpoint method, we do exactly this. So we are giving this differential equation, y prime equals f of x and y, and we are trying to solve the initial value problem, y of a equals y0. And again, you already know the routine. We divide if I want to find the function, the solution at some point b, I divide the interval between a and b to n subintervals. And in each subinterval, I try to find the y of x plus h, for example, the next point, and then I progress until I get to y of b, which is y of xn. So now I have a sequence that converges to y of b. Now for the midpoint method, what we say here is that we approximate y prime with the secant line. In each subinterval, we approximate y prime with the secant line that connects xn to xn plus 1, right? And then we have yn plus 1, and and then we say that, okay, we don't know yn plus 1, okay? And we also don't know yn, but when I start from x equals a, we know y0, okay? But we don't know yn plus 1, and that's what we're looking for. If I have the exact slope for this secant line, then I can solve this. Yn plus 1 minus yn over xn plus 1 minus xn equals the slope of the secant line. So I already know yn, xn plus 1, so I can exactly solve for yn plus 1. But the problem is that we do not know the slope of the secant line. So what we do, we use one of the theorems in calculus, in differential calculus, that says that for any continuous and smooth function, let's say this blue curve is a continuous function and it's a smooth function, so the derivative exists everywhere in this subinterval, the slope of the secant line must be equal to at least the slope of the tangent line in one of the points inside this interval. Let's call it Cn, right? We don't know where Cn is exactly, but we don't know that this Cn exists such that the slope of the tangent line is exactly equal to the slope of the secant line. All right, so we know that this Cn must be in the interval. It's most likely, in almost all cases, it's never the exactly xn or xn plus 1 unless the solution is a constant solution. It's constant, so yn plus 1 is in fact equals to yn in that case. Otherwise the cn is never exactly xn or xn plus 1. all right, and again, to refresh your memory, we're considering always a uniform partitioning when solving ODE, because non-uniform partitioning or quadrature approaches just get very complicated and they're not worth the effort. And even with uniform partitioning, we can always get very good error rate or error. We always end up with a very reliable error or very small error. So uniform partitioning is what we use for ODEs. And h is the length of each subinterval, b minus a over n, and we're looking for the value of the solution y at point b given the initial point a. Okay, so we don't know where cn is, but we can use the midpoint, exactly the midpoint of the interval, as an approximation for cn. So cn is approximately 0.5 xn plus 1. all right, but then the other thing is that now we need to be able to calculate y prime at cn at the midpoint. So y prime is f of x and y. So f of x is given, or know the x at the midpoint, which is cn, this is the prime. But I do not know the value of the function at the midpoint, right? I don't know what y of n plus 1/2 is. So for midpoints, we always use the index n plus 1/2. It doesn't really mean anything. It just indicates that we're at the midpoint of the nth interval. All right, from xn to xn plus 1, we typically use the notation xn plus 1/2 to denote the midpoint of the xn and xn plus 1. Similarly, from yn to yn plus 1, the midpoint we denote it by 1n plus half. All right, so I know xn plus half, but I do not know yn plus half. But what I can do when I put it here, I can approximate yn plus half using the simple Euler method. So yn plus half is yn plus the length of the subinterval. Now it is h over 2 times the slope of the tangent line at xn, which is f of xn and yn, which I already know, right? So this is how we do the midpoint method. So yn plus 1 is yn. So if we rearrange this, yn plus 1 is yn plus times plus y prime of cn times h, right? xn plus 1 minus xn is h. But I do not know y prime of cn because I don't know cn. So we approximate cn by the midpoint. We say that, okay, it's probably close to the midpoint. And then the y prime becomes f of midpoint x cn and y at cn. So we approximate cn, but even if we know cn, we don't know the value of the function y at cn at the midpoint. So we approximate that also using the forward Euler method. Very simple Euler method, right? It's yn plus h over 2 f of xn and yn. So we approximate yn plus 1/2 using Euler, and we approximate the cn by the midpoint of the interval. Now if you work out the math and look at the error, this midpoint ends up having an error of 1 over n squared instead of 1 over n. So this involves 2 evaluations of the f function instead of Euler method that had 1 evaluation per subinterval. We get 2, so a factor of 2. But then the error already starts from 1 over n squared instead of 1 over n. So that's an advantage. So the advantage is that the error has a better order. The disadvantage is that we need to have more function calculations per step or per subinterval. All right. Now one thing here is that if y prime is large, which means the function has a large concavity or it's a convex, all right, then this cn is definitely gets farther and farther away from the endpoints. So our approximation gets better because if we are getting farther and farther away from the endpoints, then there is a higher and higher chance that this tangent line, which has a slope similar to the secant line, becomes closer and closer to the midpoint. Now the question here is, what happens if f of x and y does not depend on y? then the solution should be an integration of the f of x from a to b, right? But what happens in this case? What do we get actually? So if the function doesn't depend on y, we remove this part. Yn plus 1 is yn plus h times f of xn plus h over 2. So it's the value of the function at midpoint, and the area underneath is being approximated by a rectangle, right? The value of the function at the midpoint times the length of the interval h. And that's exactly the midpoint approximation for the numerical integration. That's why that method is called midpoint method. Because when the function doesn't depend on y, we end up exactly with this numerical integration for the midpoint. And we mentioned that the midpoint or center approximation of the integral does in fact have a error which is h squared or 1 over n squared. Alright, so this is the midpoint method. The code is exactly similar to the Euler method. So what we did for the Euler method here, instead of having instead of having Euler sequence, we create the midpoint sequence, and everything the same. We start from x0, y0. We define the h, which is x1 minus x0 over n, and here x1 means the b, the point that we're trying to find the value of the solution. And then instead of having y equals y plus h times the value of the function at x and y, remember x and y here in each loop of the for iteration are holding the values of xn and yn, and at the next iteration they become xn plus 1 and yn plus 1. So instead of having this, we use the midpoint equation. Basically y equals y plus h times the value of the function at x plus h over 2, y plus h over 2 the value of the function at x and y. All right, we just update this one line, and everything else is exactly the same to the Euler method. And it's actually a general case here, because even if we move forward to the other methods, we only need to update this one line to implement that particular method, because this one line defines the iterations, how we generate this sequence that converges to the solution. And that's the beauty of how we implemented this way of solving ordinary differential equations in Java. So we create a sequence that converges to the value of the function at a given point, and that enables us to update the method just by updating this one line. All right. So this was the midpoint method. Almost nobody uses midpoint method because we have in fact better methods to use. So in the next lecture I'm going to talk about Runge-Kutta, fourth order Runge-Kutta, and two things we're going to see. One is Runge-Kutta, the fourth order, has a very good error which is 1 over n to the fourth. Okay. And then what we're going to see also is that the Euler method, midpoint method, they are all special cases of the general Runge-Kutta method. That's why basically everyone just uses Runge-Kutta, and nobody cares about Euler or midpoint, because midpoint and Euler are special cases of the Runge-Kutta method. All right. So thank you for watching. Please stay tuned. I have many more lectures to come, and I hope you enjoyed this lecture. I'll see you in the next one.